So, so I'd like to thank the organizer for inviting me to speak on this occasion. And I really am enjoying this wonderful place with many interesting people and also great facility. It's like heaven for theorists. And so I met Spenta exactly 30 years ago at the international school, winter school in IIT Kanpur. In fact, that was my first experience of international conference. And I really enjoyed meeting with Spenta with his enthusiastic, infectious enthusiasm and curiosity in physics, and also camaraderie. So he was involving many people, and he was so good at getting people excited about and discussing physics. And I thought that, well, outside of Japan is always like that. And so I have some photos from that time. So let's see if it works. It works. So this is me and Spenta exactly 30 years ago. You haven't changed at all. And then we had a nice bike ride to Ganga. And Professor Ramachandran is here. And so it's nice to see you again. Ramachandran was actually the chair of the organizing committee, if I remember it correctly. And so I had a wonderful experience. And many of you have noticed it, but if you go to the website of this Festschrift, there is a wonderful interview of Spenta, and I read it on my flight here. And that actually gave me a context of this conference and Spenta's physics in the background. And so it was very nice to get these things connected. So thank you for that too. And in fact, I have more stories and photos to show you. But Rajesh actually kindly asked me to give a banquet speech. So I actually am reserving those. Nothing embarrassing. But, so let's see, how am I doing with time? So after that experience 30 years ago, I have had many occasions to meet and discuss physics with Spenta, and also had some collaboration in organizing conferences in the last 10 years. Our friends in China, India, and Japan, Korea are doing the winter school in string theory. We hosted it last year at OIST in Okinawa. It went very well. It went so well, so Kavli Foundation actually decided to fund it permanently from this year on. And next year, it's going to be India. Is that going to be here? So that will be a very nice occasion again. So we are all very much looking forward to it. But let me tell you a little bit more about my scientific experience in India in 1987 and the follow-up of that. It turns out that 87 was also the centennial of Ramanujan. And so this is a Ramanujan lecture hall. So this will be a nice venue for that. So in that year, maybe a year before, George Andrews actually, who this book of Ramanujan, archived it and edited it and published it a year before. And there was actually a TV program of Ramanujan's Lost Notebook. And I remember during the winter conference, we watched the TV program with Gautam Mandal and Smith Das, and maybe Spenta was there too. And so we were joking, so it was about mock theta function. And so we are joking that maybe someday it will be useful for physics. And there is actually a more elegant version of saying that at the proceeding of this Centenary conference by Freeman Dyson, that says that mock theta function gives us tantalizing hint of grand synthesis still to be discovered. My dream is that I will live to see the day when our young physicists struggling to bring the prediction of string theory into correspondence with the fact of nature will be led to enlarge the analytic machinery to include mock theta function. And in fact, Freeman didn't have to live long. He actually, of course, lived very long and he's still living very strongly, and so it's wonderful. But it turns out that just a year afterward, its application to string theory was found by Eguchi and Taormina in the context of n equal 4 superconformal theory in 2 dimensions. I was very impressed by this, and then thought that, well, we can use that to understand K3 sigma model better, because that's the symmetry principle of K3 sigma model. So I worked with Toru Eguchi and Taormina together with Sunkiru Yan, And we studied various examples of n equal 4 superconformal sigma model, Gepner model, and orbifold. And we found that there is always a part of the spectrum that is generic and is identical in all examples. And we didn't understand what it was for a while. And then realized that this part is actually counting the quarter BPS state, and so therefore is invariant under perturbation. And this turned out to be what is now called the elliptic genus. This was what we calculated. And in my PhD thesis, actually, one of the main things was I calculated this elliptic genus and expanded it in this n equal 4 character expressed in terms of mock theta function. And I got all these positive numbers. And there were some reasons that these physically interesting things that has to do with these integers all being positive that I do not have time to explain. But that was my PhD thesis in '89. I didn't understand what these numbers meant. But it turned out that it has various applications. So for example, more recently I used with Christoph Keller the elliptic genus to put some constraint on the non-BPS spectrum of K3 sigma, various Calabi-Yau sigma model using a conformal bootstrap combined with constraint coming from elliptic genus. And but these numbers were still mysterious and kept bothering me. And one day in 2009 in Aspen, we actually realized that if you divide actually all these numbers by half, by 2, then this becomes actually the dimension of irreducible representation of Mashu group. So this was this is what is now discovery now is called Mashu moonshine, where this elliptic genus seems to have some hidden symmetry of Mashu group, one of the large sporadic finite group, M24. So actually, last year, David Tong kindly invited me to visit Wren Library of Trinity College, where the Ramanujan's last letter is located. And in fact, you can actually ask the librarian to open it up and then look at it. And then this is the last page of the letter, and you can see that in this equation, you see exactly the character of n equal 4 superconformal. It's a nice thing to do. So there is but there is still a mystery of how exactly this M24 is realized in the context of K3. And there is an interesting work by Matthias Gabardiero and the collaborators saying that there is no single K3 sigma model where M24 is a full symmetry of sigma model. But that's not what we conjectured, because what we conjectured is that M24 is actually symmetry of quarter BPS spectrum. So I think that what is interesting possibility is that it is a symmetry of this quarter BPS spectrum. And but then there are various consistency checks that we could consider doing. So for example, if you consider moduli space of K3, at each point there is a K3 sigma model. So there is a space, vector space of quarter BPS state. As you move in the moduli space of K3, this makes non-trivial bundle. And in fact, you may consider computing curvature. So one natural conjecture is that holonomy of this quarter BPS bundle over moduli space of K3 commute with M24 action. So that would be a natural conjecture that I would like to try. So I'm actually working on this program. But today, I would like to discuss a little bit more modest issue on the base of K3 moduli space. And in fact, there has been some paradox about K3 sigma model that has been, this is another thing that has been, yes. So there is a holonomy of a quarter BPS bundle that you can compute. Yeah. So if the M24 is a symmetry of a quarter BPS state, then M24 should be a commutant of holonomy of the quarter BPS bundle. So that would be one way to formulate our conjecture.
You don't have an action on the base there.
You ask, no, that would be moving the K3 sigma model. So that I wouldn't call that as a symmetry of sigma model. That would be my tentative way of formulating the conjecture. So there has been a paradox of the base K3 sigma model for about 27 years. So this is what I would like to talk about today. So there are actually two interesting papers in late 80s that has to do with moduli space of Calabi-Yau in the context of string theory. One is a paper by Seiberg, where he pointed out that if you consider stringy effect, then the moduli space of K3 is a coset of O4, 20 divided by O4 times O20. So this is a very beautiful result, enlarging what was known in mathematics. But a year later, there was a paper by Dixon, Kaplansky, and Lewis, which is also very influential, that said that this is discussed in the context of Calabi-Yau threefold, but applied to other Calabi-Yau manifold, that the moduli space actually split into product of Kähler moduli space, Kähler manifold, one of which is associated to vector multiplet, and the other is related to hypermultiplet of Calabi-Yau compactification. So these two statements contradict with each other because K3 is an example of Calabi-Yau. However, the moduli space conjectured by Seiberg and in fact verified by many ways, this is not Kähler, or it doesn't even factorize. Because this is actually an example of one of the Berger's classification of symmetric space. And this is irreducible, so it doesn't factorize, obviously. So actually, in this talk, in the remaining 13 minutes, I will resolve this tension between the two papers. And this turned out to be due to a new type of anomaly that was not known before. This is based on my paper with Jamo Gomis, Zohar Komargodski, David Tong, and Wang. And so the question again is that in general, the moduli space split into moduli space of chiral multiplet and twisted chiral multiplet, and both are Kähler. And these are prediction of this. On the other hand, if you look at some simple example like torus or K3, torus is in the case of work by Narayan, both of them are symmetric space like that, and neither factorize, and neither of them are Kähler. So what's going on? Why these are not special example of Calabi-Yau? Well, one thing that you immediately say is that R-symmetry is enhanced. In generic Calabi-Yau, you have n equal 4 supersymmetry, and you have U1 R-symmetry. In these cases, actually, R-symmetry is enhanced to non-abelian symmetry. But that by itself is not an answer. It's a special feature of this example, but why they contribute to violation of this principle is not understood. Because normally, when particular global symmetry implies special property of the model, then enhancing that symmetry does not ruin those properties. If symmetry has anomaly, that would ruin it, but simply enhancing the symmetry should not ruin that property. So what's going on here? Well, one thing you may notice is that if R symmetry is enhanced, there is a special operator with some R charge, in this case, for example, 2, 0. And so that means that there is actually a new type of operator product singularity between chiral primary field and twisted chiral primary field of this type, because if you look at the charge assignment and weight assignment, existence of this R charge current allows this OPE. And in fact, you can show that if R symmetry is non-trivially enhanced by this charge current, then you have to have non-zero pairing like that. You can also prove that. So in the case of K3 sigma model, this is how it is realized. So I don't have time to explain it, but you can actually check explicitly in K3 sigma model that you have this type of new OPE singularity. It's actually useful to write it in the context of n equal 2 superspace. So you have this chiral multiplet field phi and twisted chiral multiplet phi tilde. So you upgrade that to superspace field. And also this extra R current, the additional R current, becomes part of what is called very short multiplet, because this is both chiral and twisted chiral. And then using that notation, you can write this OPE in superspace like that, where this is a supersymmetric combination of these coordinates. In fact, there is some slight twist to the story, because you can always add counter terms in the OPE when it is allowed by symmetry. And in the case in question, supersymmetry allows adding this counter term. And we have actually shown that these are the only contact term that is allowed in this case. By adjusting this, you can actually change the OP singularity slightly, but you find that whatever choice of C you make, you either break the condition that d bar, so d bar should be annihilating, oh, this is a chirality condition. But in the presence of other operator, this chirality condition can be violated by contact term like that. Or if you adjust this term C, then you can make this to be non-zero. But you can show that whatever choice of C you make, it is not possible to set both of these to be zero. Namely that if you have some another operator, then one of these conditions gets violated. Well, what it means for the factorization program? Well, one nice way of proving the factorization of the moduli space and Kähler condition, etc., is to use what is called the Spurion technique. That is the idea that when you do the marginal perturbation by this operator, you have this coupling constant lambda multiplied to the marginal operator. In this case, these are marginal operator in the superspace. Then the idea of Spurion analysis is to upgrade this lambda and the lambda tilde, the coupling constant, to background chiral and twisted chiral superfield, and then use the superspace constraint to find the possible term in the effective action. And this is a way that, for example, the Seiberg, this group of people proved this theorem from the worldsheet perspective. This method fails in this particular case because presence of this contact term implies that if you upgrade this coupling constant to be superfield, then d bar equals zero condition is modified by this term. Or depending on the contact term you add here, which corresponding to adding counter term over here, you can have this condition violated. So that means that as soon as lambda or lambda tilde becomes superfield, the chirality condition on this field gets violated. So this is what we call shortening anomaly. Then this does look like the form of anomaly, namely that anomaly means that current, which normally should be conserved, have non-zero value for the divergence. Similarly, here we are finding that if you upgrade the coupling constant here to be twisted or the chiral or twisted chiral superfield, then the chirality condition, which normally should be equal to zero, becomes non-zero because of this. In the case of anomaly, what you usually find is that when you couple the gauge source, the current to source, and make the source to be the position dependent, then you get non-zero divergence. So this situation is very similar to that. So this means that the marginal coupling of lambda and lambda tilde, which move the theory in the moduli space of K3, cannot be promoted to background superfield in short representations simultaneously. So that means that the result of this Spurion analysis is invalidated, and therefore this factorization proof fails. So I found it very interesting because, to my knowledge, this is the first instance where the Spurion argument fails to work. Spurion argument has been a very powerful method in proving results in supersymmetric theories. Plays very important role in discovery of duality between various gauge theories, etc. But it seems like this is the first instance where there is actually a loophole in the application of Spurion analysis. And it would be interesting to find out whether there is a higher dimensional generalization of this type of anomaly. You can also understand it from the point of view of Bess-Zumino consistency condition. So namely that in this case, what you do is since now suppose you consider this not as a chiral perturbation, but Kähler type D-term perturbation. And then this can be reduced to this type of perturbation if there is a symmetry to the parameter here. And it turns out that you can actually have this kind of anomaly term, which is cohomologically non-trivial in the sense of Bess and Zumino. And this term exactly corresponds to this type of anomaly that I talked about. And so unfortunately, I'm running out of time, so I do not have time to explain it. But you can, what I wanted to say was that just like in the ordinary gauge anomaly, or you can understand this new type of shortening anomaly in the language of Bess-Zumino cohomology analysis in the field space. You can also ask what happens to the idea that if you just reduce the program to the n equal 4 supersymmetric theory is an example of n equal 2 supersymmetry. So why is the standard n equal 2 argument does not work? So here is another perspective of this. So as I said, the presence of enhanced R-symmetry of supersymmetry implies this new type of OP singularity, which means that actually there is a mixed curvature of this term. So from that, you can immediately see that since there is a mixing of curvature in this direction and in this direction, so the factorization fails. But there is another perspective that you can make. So suppose, for example, you consider n equal to suppose you consider particular K3 sigma model. So you have n equal 4 supersymmetry. You decide to choose n equal 2 subalgebra and say that, well, we can write word identity for the n equal 2 algebra, and therefore you can prove factorization. But what happens is the following. On each point in K3 moduli space, you have to make choice of n equal 2 subalgebra in order for the argument to work. So the question is that, can you make consistent choice of n equal 2 subalgebra through the K3 moduli space? What you can show using this type of calculation is that you can think of you can calculate how the n equal 4 superconformal generator, and in particular n equal 4 supercharges fiber over base of K3 moduli space. Namely, you can consider supercharge bundle over moduli space of K3. And you can show that it is not possible to consistently choose n equal 2 subalgebra within n equal 4 subalgebra. Whichever n equal 2 subalgebra you make, as you move moduli space and come back to the same point, you always get a different subalgebra. So that happens even in the small neighborhood of a given point, because the curvature, so it's a homogeneous space, so curvature is essentially the same everywhere. So that's another way to understand why the standard n equal 2 argument fails in this context. So there are various different ways to understand why the factorization fails. But the essential thing is that there is an anomaly. This also gives you some practical applications. So this is actually very similar to the idea of two-Hooft anomaly matching condition. So suppose you have n equal 2 renormalization group flow, which respect all marginal coupling. So that means that there shouldn't be shortening anomaly, because shortening anomaly means that this n equal 2 chirality constraint gets violated. So that means that since n equal 4 sigma model has shortening anomaly, so whatever ultraviolet realization of this K3 sigma model must have that property. In fact, this saves us lots of work, because there has been lots of work being done to try to discover that n equal 2 gauged linear sigma model, which UB complete to K3 or T4. And nobody succeeded in doing that. This work explains why it is not possible. Because if it was possible to construct the gauged linear sigma model for K3, which in the infrared flows to K3 sigma model, then since this gauged linear sigma model does not have a shortening anomaly, so that means that K3 sigma model should not have shortening anomaly, which is a contradiction. So that means that there has to be no such thing. Of course, within the subspace, you can construct such example, but within the subspace of the moduli space, so you can have an example of K3 sigma model, linear sigma model, which realize some subspace of the K3 moduli space, but there cannot be, there shouldn't be a gauge sigma model which covers entire K3 moduli space. Except if you can actually make sense of n equal 4 linear sigma model, you can do that, but we don't have such formalism yet. So for on the other hand, there are examples of T2 superconformal field theory, like this, which covers the entire moduli space. And the reason for you can do that is that in this model has exactly n equal 2. There is no enhancement of supersymmetry. So as soon as you have enhancement of supersymmetry, then you have this type of problem. So this matches up very nicely. So that's all I wanted to tell you, Spenta. So for now, until the banquet. So thank you very much for your friendship for the last 30 years, and I hope this will continue for many more years to come. Thank you very much. Happy birthday.
Thanks, Hiroshi. Questions?
So if I understood correctly, that right on the first or second transparency, there was some argument by Seiberg that
Yes.
the moduli space had to be this coset space, which is not K.
You're referring to, yes.
Yeah.
Right.
And so I can't remember if he was thinking of it this way, but that result would just follow from compactification and the allowed moduli spaces.
Excuse?
It would just follow from looking at...
You're asking, you're referring to this result.
Yeah.
That the moduli space being coset.
Yeah,
Yes.
I think he derived it from superconformal field theory, but maybe in that paper or shortly thereafter, it just comes out of looking at allowed theories of supergravity in 6 dimensions.
Yes, that's correct.
So just right from there, there's already a puzzle, right? Just from that point, the fact that this moduli space is not Kähler, there's already...
You mean from the supergravity perspective?
Yeah.
Yeah, but from supergravity perspective, there is also a way to understand it, and that's relatively simple, which is that n equal 4 supergravity is not an example of typical n equal 2 supergravity.
Right.
Because from the if you decompose, so you can say that so n equal 2 field theory, n equal 4 field theory is an example of n equal 2 field theory. So for example, whatever that is true for n equal 4 supersymmetric field theory is true, whatever that is true for n equal 2 supersymmetric field theory is true for n equal 4 supersymmetric field theory. But that's not the case. That there are certain things about n equal 2 generic n equal 2 supergravity theory that is not true for n equal 4 supergravity. The reason for that is that n equal 4 supergravity have 2 gravitino multiplets, which usual n equal 2 supergravity don't have.
So already from supergravity, one could see that there had to be some subtle puzzle, which you've just elucidated,
right,
in the two-dimensional field theory. Would the same thing be true for Calabi-Yau spaces? Because their moduli spaces also take some funny form that is special geometry that when you include the dilaton that wouldn't...
You mean that, for example, the hyperkähler becomes quaternionic Kähler?
Yeah, and they're not right. Yeah. Is that a higher dimensional? Must there be?
I think it's a slightly different nature. I think because field theory, so there is a effect due to purely two-dimensional nature, and then there are some additional space-time effect coming in understanding. So this issue was purely field theory, two-dimensional field theoretical phenomena. And that's why we were able to explain it in terms of anomaly in 2 dimensions.
I see.
And the situation is slightly different for the case that you were mentioning.
I see.
Okay. If there are no further questions, we break for tea right now. So let's thank Hiroshi again.